from the limit comparison test, we get the rational function test. So recall, a rational function, say r of x, is just going to be the ratio of two non-zero polynomials. So I have a p of x, I have a q of x, and neither of these is exactly equal to 0. So rational function test just says let a sub n be equal to p of n over q of n, as above here. And when I sum up, we're going to have n large enough so that we bypass all the zeros of q. So we don't want to divide by 0 here. Otherwise, it won't make sense. Then, if I take the series associated to a of n, we're in 3 cases. The degree of p is bigger than the degree of q. We're going to diverge. If the difference between these two is exactly 1 and the degree of q is bigger, we're going to diverge. And then, if the degree of the bottom beats the degree of the top by 2 or better, the series will converge. All right. The important idea here is the principle. Let's take a look at some things that we have here that we need to be careful with. Note that if I'm going to use the limit convergence test, we have to have that we have our 2 sequences we're going to compare the series of. The terms on both of these are going to have to be positive numbers. Now, to make this work, we'll just assume if I write out my p and q in terms of sums of powers of x, they're polynomials. We're going to assume that the leading terms on each of these are going to be positive. That's not a problem. If one of them was negative, we can just change it to a positive by multiplying by -1, and they can pull that minus sign out in front of the summation. So that's our first thing to fix up. Next thing we want to fix up is, well, I'm looking at a polynomial, so that thing can go above and below the x-axis, throwing out negative terms. That's not a problem either, because remember, for most of our series tests, we don't need to consider every single point in the sequence. We're allowed to throw away finitely many for purposes of the test. So when I consider what's happening for our rational functions, well, for the polynomials, we can just ignore everything until we have both of these positive, which they will be, because if their leading terms have positive coefficients, the limits as we go out to infinity are going to go up this way. And so at some point, we leave the x-axis forever. So this is all just going to say that the limit comparison test is a valid thing to use to check for convergence of these series. Let's look at some examples. Okay, let's try n going from 1 to infinity, sum n squared plus 1 over n. The degree on the top is 2, degree on the bottom is 1. So that means we're going to have divergence if we believe the rational function test. Also note, if I take the limit n goes to infinity of the sequence, I have n squared plus 1 over n. If I divide top and bottom by n, I'm going to have an n plus a 1 over n. So the sequence itself is going to go off to plus infinity, which means it's going to fail the limit test for divergence. So this is going to diverge by the first test we should actually use on any series. My next example, let's consider sum going from 1 to infinity, n over n squared plus 1. I squint at this, I notice 1 over n pretty much looks like this. This looks like n over n squared, so that's going to collapse to 1 over n. We know that this diverges because it's a p series with p equal to 1. So I choose my b sub n equal to 1 over n, and we're expecting that this thing's going to diverge. Take the limit of an over bn as called for by the limit comparison test. It's going to give me n over n squared plus 1 over 1 over n. We multiply through by n squared plus 1, top and bottom. Clear out those denominators, and that leaves me with n times n over n squared plus 1. To clean that up, I'm going to divide top and bottom by n squared. It's going to give me 1 over 1 plus 1 over n squared. As I go out to infinity, the 1 over n squared goes to 0. So our limit is going to be equal to 1. Limit comparison test then says, since I have a finite number that's non-zero, not infinite, we're going to have that these two series converge or diverge together. Since 1 over n diverges, that means both series are going to diverge. So divergent. My next case, this is going to be our third case, of n squared plus 1 over n to the fourth minus 6, sum going from 1 to infinity. We squint at this, and we notice pretty much looking at sum of n squared over n to the fourth, which is roughly sum of 1 over n squared. So again, we're looking at a p-series, but here we have p equals 2, so that's going to be in the range of convergence. All right, if we compare what's happening with the degrees, actually in our last one, the degree differed by exactly 1. Rational function test says we diverge here. Here, we're going to have the degree in the bottom is bigger, and the difference is 2, which is bigger than 1. So we're expecting that this converges by the rational function test also. All right, we'll use the limit comparison test to run through this. So let's check. Take my an over my bn. Okay, this is our an. Our bn is going to be the 1 over n squared. We have this over this. I'm going to clean it up by multiplying top and bottom by n squared, n to the fourth minus 6 over itself. That'll collapse things to an n squared times n squared plus 1 over an n to the fourth minus 6. Then I'll divide top and bottom by 1 over n to the fourth. Okay, and somebody should multiply that out. And so that's going to leave me with a 1 plus 1 over n squared, 1 over 1 minus 6 over n to the fourth. And so this goes to 0, this goes to 0, leaving me with a 1. And so they're going to both converge or diverge together by our limit comparison test. Since our b sub n goes with a convergent series, they're both going to converge. Why is the rational function test true? As we've seen in the examples, it's going to follow from the limit comparison test. So let's write our polynomials as Pn over Qn. Pn has lead term ck n to the k and a bunch of lower stuff. And then Q of n will have lead term d to the l, n to the l, and then a bunch of lower power stuff. So if I squint, I'm going to choose my b sub n equal to n to the k over n to the l. Then we're going to apply our limit comparison test to these two sequences, a sub n over b sub n, where a sub n is our original sequence. Take the limit as n goes to infinity. So this is a sub n, this is b sub n, and I want to clean this up. I'll clean this up by multiplying top and bottom by n to the l over n to the k. That's going to take out whatever's in the bottom, and then I just have to collect the stuff on top carefully. So first thing I'll do is I'll put the n to the k with the cknk. That's going to look like this. And then if you notice, for my bottom term, so we've gotten rid of all that, if I want to put this underneath, I have to flip that under. So that's going to give me d to the l, n to the l, plus lower order stuff over n to the l. So I can now take the limit of this, and we notice the n to the k is going to divide into the first term exactly, leaving me with a ck, and then all the other terms will be constants times 1 over n to a positive power. As I take the limit as n goes to infinity, all of these 1 over n to the positive powers are going to drop out going to 0. So I'll be left with ck. On the bottom, same idea, except here we'll be left with d sub l. So our limit's going to be c sub k over d sub l, and that's going to be non-zero because we're assuming that our polynomials are not exactly equal to 0, which means there's going to be lead terms which are non-zero. Okay, so that's going to say that our original series is going to converge or diverge together with this n to the k over n to the l series. Let's take a look at when this converges or diverges. Well, if the degree of the top is bigger than the degree of the bottom or equals, what's going to happen here? That's just saying the k minus l is going to be either 0 or it's going to be positive. If it's 0, we get a 1. If it's positive, we're going to get n to a positive power. The limit of that as we go out to infinity is just going to go off to infinity itself. So that's going to say the limit of this thing is going to be non-zero. So our limit test for divergence says if the limit of the actual sequence is non-zero, then your series is going to have to diverge. So that takes care of our case where degree of the top bigger than degree of the bottom or equals. Okay, diverges. Otherwise, the degree of the top is going to be less than the degree of the bottom, and then we're looking at a p-series. So if I put things in the bottom, I'm going to switch the order of the k and the l, so that becomes l minus k. Our p is equal to l minus k here, and then we just push things through our p-series test. Well, I'm going to diverge when L minus k is between 0 and 1 is inclusive. So pulling that apart, we just push the k to the other side. That's going to say L is less than or equal to k plus 1. But notice, this is just saying the degree of q and the degree of p differ exactly by 1. Because we have integers, I don't have to worry about filling in the numbers in between. So here, we're talking about a p where we're between 0 and 1. So that means we're going to diverge. So if the degree between the two is exactly 1 and the bottom is larger, then we're going to have divergence of our original series. If we consider the other case where L minus k is bigger than 1, then we're going to have convergence because p will be bigger than 1. And then we're looking at when degree of q is bigger than strictly the degree of p plus 1. But all that's saying is that the difference between the two is 2 or larger. So we had convergence when I'm looking at the difference in the top and bottom by 2 or bigger. Now, you can modify this test to deal with the fractional powers, but just remember you're not going to be dealing with this sharp boundary at 1. The difference won't be strictly 1. It'll be a number that's less than 1. Okay, I'll leave that as an exercise to figure out. And also note that when you're messing with these types of things, it's always a good idea to get all your exponents in terms of positive powers. So for instance, if I had an n to the minus 1/2 in there, you will multiply your top and bottom by n to the 1/2 just to get that thing out of there.